Okay, got a nice question now looking at longitudinal waves, sound waves. So let's go through this. Diagram below shows two students P and Q trying to measure the speed of sound in air. So the speed of sound in air is about 330 meters per second. You'll see later on it changes on a cold day, on a warm day, that speed will change. So P's going to clap their hands, and you can see they've got them in a little clapping action there. When Q sees them, they're going to start a timer. So I'm going to put a stop clock here, and we're going to see, well, there's a problem. We've got human reaction times. So I'm just going to box that there. And when they hear the clap, they'll stop. It says, how could they improve their method? I'm going to go in the diagram, and I'm also going to highlight that. So the key thing they're going to say, how could they improve their method? Well, clearly, human reaction times. So just write that there, human reaction times, due to using a stop clock, is going to massively increase the percentage error in this. And the fact we've got 50 meters, you can imagine it's taking far less than, well, what's that, about a third of a second, something like that, to go that distance. So human reaction times are going to be massive. And then that's a problem. So we're going to now have a look at, well, what could I do? I can increase this distance so there's less percentage error, or I can, due to reaction times, or completely remove human reaction times. And how can I do that? Well, I could use a microphone here and here and connect it to a data logger that does it for me. So we're going to see that that's one way of improving it. And the second way is use microphones and a data logger. And you can talk about either one. The crucial bit in the questions is it says here, explain. So reading questions is a really important thing. So not only have we got to say, what could we do to improve it, but then how does it improve it? So I'll go with the first one here, and it's nice and easy. Well, increase that well past 50 meters. And we can see if I want to get, say, 2 seconds gap, I'm going to have to go to at least 60 meters. So, I want it greater than 600 meters. I said 60 earlier, but you get the idea. So, and that would reduce the percentage error due to human reaction times. Remember, you write it in full, but that's that part. And I've got a mark there because I've said what I'd do. Increase that distance. 50 meters is too short. And how would it do it? It would reduce the percentage error. Now I'm going to go on to number 2. And that is swap the manual timers for 2 microphones and a data logger. And what would this do? This would remove the error due to human reaction times. Happy with that? So that helps. Go on to the next part. We've now got a hammer and a rod. We're going to cause a sound wave to travel along it. So what do we know about that? Energy is going to go that way, and the vibration is going to be, so that's the vibration V, is going to be parallel to it. How does it occur? Because it's a sound wave. Well, the particles will vibrate. Their vibration will be passed on to the neighbouring particles, and then that will propagate across the metal rod. Now, ultimately, if I was to say zoom in here, well, we know that the particles in a solid are close together, moving in sort of fixed vibrations randomly. If I was to zoom in and zoom in and zoom in and zoom in, well, due to this vibration, we would see that there are small gaps between those particles. This is exaggerating, by the way. Don't ever draw that for a particle diagram. So when I cause a vibration, these particles are going to move close together. So we're going to have a place where the particles are relatively closer together. And then we're going to place where these particles are relatively further apart. This is called a compression. This is called a rarefaction. And that's it. So I'm going to be talking about the fact that this is a longitudinal wave. We're going to start a vibration going. It's going to be parallel to the direction of the energy. This is going to cause the particles to vibrate. So I'm going to have a keyword there beginning with P. And those particles are going to pass that on to the neighbouring particles, causing compressions and rarefactions. And there we go. So that's it done verbally. I'll do the slow bit of writing it all out. So the hammer causes a longitudinal wave where the vibration is parallel to the direction of energy transfer. Okay, so the metal, use capitals for this, particles, transfer the vibration to neighbouring particles. This causes compressions and rarefactions. Now you'll see in the mark scheme, great big chunks of this aren't in the mark scheme, but I've just given you a model answer that you can use for any sound wave. And sometimes in exams mark schemes, you're kind of playing a game of what do you exactly want for this mark scheme. That covers any of the mark schemes I've seen so far. Okay, the next one, sound travels, and it's got a clear part here, slower in air than it does in water. So now I can go, well, it's going to go fast in this, and it's going to go slow in this. The sound wave refracts at the boundary, so it's going to bend at the boundary. And the crucial part is we've got to decide, is it going to bend that way or is it going to bend that way? Okay, so I've tried to teach you, sketch yourself a little car, get yourself a rubber or a pencil sharpener, and then brum, 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 brum along the line. When we get to here, we can see side A hits first. So that's going to slow down. So you can imagine now, here's my car. This end's going slow. That's going fast. And you can see it's going to bend towards north. So now I'm just going to draw with a pencil and a ruler. That. And we can see that it's refracted towards the normal. But you can see, crucially, that was really important to read. It's not a light wave. It's even telling you a sound wave there. Going on to the next one. It says, we've done that, tick. The last question. So this is just an example of, can you manipulate an equation? They're not expecting you've learnt this equation. It's not in your equation sheet. They're saying, well, you're given this, use it. Now, we've got a unit after Christmas where we're going to be looking at constants a bit more, but I know you do them in maths. So it's telling us K is a constant. Now, my general rule of thumb is anytime they tell you there's a constant, I want you to always do, number one, you're going to have to find out what K is. And then number two, once you found out what K is, you're going to have to use K. All right. And we can see we're going to have to find out K using this line. So that's number one, find out K. And then this part here, that's the use K. So now I'm going to just get rid of all of that. And we can see what we've got to do. I'll teach you the kind of dodgy way to rearrange, but it's certainly one way. We can see we've got 1, 2, 3 factors. So I'm just going to do my typical get a triangle. I can see K is on top, so K's got to go there. Speed of sound in there. And the square root of the density goes there. That's the symbol for density, but I'll teach you that later. But I'm more than happy if you do square root of D. But I can't do that, it's bugging me. So that's going to go there. Well, now I can see K is the speed of sound divided by the square root of the density. So my first job is, let's go and find out K. So part one, zoom in here. So part one is find or calculate K. And we said K equals, got that there, speed of sound divided by the square root of the density. Equals the speed of sound divided by the square root of the density. So now I can pull this out here. K equals 331 divided by the square root of 1.29. Put that in my calculator now. 331 times the square root of 1.29 equals 375.9 and loads of other numbers. So I can put in brackets here, 376. I'm going to keep the number of my calculator there because it's there. So we've now worked out K. Now I've got to use the value I worked out to k to get the speed of sound. We can see speed of sound equals k over the square root of the density. So next part 2, use k. So the speed of sound equals, and I'll go back up there to remind you, k, which we worked out. So we're going to bring this value down, divided by the square root of the density, equals k divided by the square root of the density equals, I'm going to put 376 in there, but I've left the value of my calculator, divided by the square root of 1.16. And you can see I'm using this value here to get that value. Put that into a calculator, and when you do, you get 349. All right, and it says to significant figures, well, if I'm measuring this, 3 significant figures will be perfect for this. 3 sig figs. Okay, going on to the next part. That's it. Brilliant. Recording has disappeared. Oh no, don't lose out. No, yes.